Hello, my name is Yarub Al-Haj. This is a presentation regarding the assignment for engineering mathematics. I'm going to be presenting three main problems that were presented in this assignment. So the first one is about a cylindrical tube. So we are tasked to design a cylindrical tube for mailing A4 papers, and we are given some dimensions. So we're given the volume, we're given how much each side is going to cost. So before we get into that, so we know we need to basically optimize the cylinder so that it costs the least amount of money to make it. And how do we do that? We need to know the height of the cylinder, the minimum height, the least amount of height. Okay, so because the height has a cost, right? Or like another height, like the side, yeah, the side has a cost. And the end caps also have a cost. So this is the cost of the end caps, and this is the cost of the sides. And so we want the least amount of square meters per each one of those to house to house this volume. Okay, and in order to do that, we can come up with a function. But before that, so the area of the each side to figure out the area of each of the end caps, it's just the area of the circle multiplied by 2, since we have two end caps, and then the area of the side is going to be the normal area of the side. So where is it? 2 pi r here, 2 pi r times h, right? And we know this from the cylinder area formula right here. And yeah, so besides that, uh, so we have these we have these information so far, and so we're going to create a function that tells us how the cost affects the sides per meter, you know. So we say that, okay, we assume that cost per meter side multiplied by the area of the side multiplied by the cost per meter of the end caps, multiplied by the area of the end caps. So we keep the area in mind for each one of these because each meter costs money here, right? So we want the least amount of that. So we multiply the cost here, multiplied by the area of each of these, the side and the area of the side, the area of the end caps. However, we have some missing values here, so obviously we don't have the radius and we don't have the height. And those are the two main factors that affect the cost. And so we try to find the height first. So we have the volume. So since we know the volume, we can find the height easily. So okay, and so so the height is equal to 0.010, which is the volume, divided by pi r squared. Okay, we just rearrange this formula. Okay, we took so it's just a normal equality, right? So we know that the v, we take this to the other side, and we take this to this side, so that we can find the h. Okay, next, we rearrange that into the formula. So we substitute that back into the formula in order for us to have only one variable, which is the r. Now it's easier for us to find the r. So we still don't have the r, but in order for us to find the r here, we need to take the derivative. Okay, we need to take the derivative of the r, and so of this function in general. And so to make it simpler, we replaced it from this form into this form. Okay, so now it's kind of easier to to do the derivation here. So we do the derivation, we get this 2 is multiplied here, and this should be 2. Okay, this should be 2. So this is 0.36 to the power r to the power of -2, and this is going to be -1, since the -1 goes here. And then after that, we bring it back to its original form. So now it's over r squared, and yeah, we got this. And the next, since we need to find the least amount of radius that we want, okay, the minimum amount of radius. So we use a stationary point rule. So we take the zeros of this equation. So we equate it to the 0, and then we take this to the other side. Now it's both of them are positive. Okay, so now we just try to isolate the r. So we just rearrange the formula here so that it's in terms of r to the power of 3. And then to get rid of the power 3, we just take the cubic root of both sides, and we get the final answer, which is 0.1 meters squared, which is the optimal radius. And so after that, since we got the optimal radius, now we can get the height, which is substituted back in the previous formula for the height, this formula right here. Okay, we substitute the r here, and we have the pi already, and we get the height, which is that. Okay, This is per square meter, okay? And then after that, since we have the height, we have the radius, we can just substitute them both back into the original formula, and we get our C minimum, which is the minimum cost to spin. So we have the radius, we have the height, 10 centimeters in radius, roughly 31 centimeters in height, and 5.36 minimum cost, okay, which is in ringgits. Okay, so the next problem presents us with a billboard that is behind this mailbox. So this billboard is affected by the wind. So the wind is blowing on it with pressure. So we have these dimensions for this billboard, which are the width and the height, okay, which are extremely essential for us to calculate. And we have a pressure, a formula for the pressure here, and we have a formula for the force. Okay, so for us now, firstly, obviously, we need to, in order for us to find the pressure, and like the specific pressure that's going to be applied, we need to find the force first, right? So the main pressure that we need to find is the center pressure. So to find the center of pressure, we first need to find the force, and then we need to find the pressure. Okay. So the force is represented by this given formula, and we just simply substitute the numbers were given. So we substitute the height and substitute the width here, and through that we just do normal integration, and taking the 5 outside of the integration, and then we integrate. So this is just the opposite of derivation. Normal things here. So to the over 2, and then becomes to the power of 2. 2 divided by 1. This is going to be 6. Okay, and it's going to be 2. Yeah, just normal derivation. Yeah, and then we get this value right here. So after we substitute a 4 and a 0, we get this value. So which is 1,280 Newton. And before we finish this, we need to find also the moment. So in order for us to calculate the pressure, so the moment is represented by this formula, which is quite similar. The only difference is that we have the y factor here. And so by using like this extra y in here, so multiply it inside, and then we take the integral, right? So now it's a little bit different since we multiply the y inside. Now it's y squared and y power 3, right? And so we take the derivative. We take the integral of those. So it's quite simple. Same thing here. So like over 2 over 3, and then we simplify it, and then we get the integral. We substitute the 4 and the 0, and we get the final moment, which is 2,880. Okay. So in order for us to find the pressure, the center point pressure, we divide the moment by the force, and we get this center point for pressure. Okay. So to represent this, so like, what if we say that the YCP, okay, YCP, which is this, or the yeah, PY, which is PY, is equal to YCP. What is that going to mean? So this is going to mean that the pressure is at this exact center point. So the exact center point, this is the billboard, okay, for example. Okay. So the center point, we have the height of this, which is 4 meters. Okay. So the center point is at the center here, which is at the 2 meter mark. Okay. At the 2 meter mark, here, this is going to be the center pressure. But since we found, so if the pressure at the center is going to be divided equally at both sides here. But what we found here is that the center of pressure is not actually in the middle. So the center of pressure is going to be here, okay, somewhere at 2.25. Yeah. So at 2.25, this means that if we look at the billboard from the side, okay, if we look at it from the side, it's going to be a little bit tilted, yeah? So we're going to have the force being applied from the top here, a little bit away from the center. So this is going to tilt this to this side more than this, which is going to mean that the pressure being applied here at the top is higher than the pressure applied at the center. Okay, so therefore, the pressure at the center pressure, YCP, is going to be lower. Is going to be lower if YCP was equal to PY. Okay, And so this is quite simple and straightforward. And let's oh, finally we have one more problem. So we're trying to basically improve on our first design for the cylinder, right? So our first design for the cylinder was good, but since we have developed more efficiency, more error decrement uh, function, so this error decrement function is going to help us to decrease the error of the design. Okay, so the givens here are the initial error, which is which is 5%, and then our target is to decrease the amount of error to 0.5%. Okay, or less than 0.5% actually. And then the reduction rate that we are given is 60%. And the time, okay, we're going to do this later. So the time is like 20 minutes and 10% faster each cycle. Okay. So what does this tell us? So this can help us formulate a formula. So we know that the initial pressure and we know the target and we know what are the factors that we're decreasing by, right? So we know that the initial is 0.5 is 5, okay, 5%, okay, and we're going down by 0.6%, but we don't know how many times are we going to go down until we reach, and this needs to be less. This needs to be less than 0.5, okay? And for this to be less than 0.5, we need to know how many times we need to reduce the 5% by 60%, okay? So this is going to be our n. So we need to figure out the n here, right? And so that's exactly what we did here. So we got the inequality, and then we basically divided both sides by 5. So we got 0.1 here, and then this, and then we took the special algorithmic rule. So we took the ln of both sides so that we can take the n outside. So using this specific feature of algorithms, we were able to separate the n on its own. So we put it in this side. After taking the logarithm of both of these, we found that they're both negative. So taking this to the other side will flip the sign, the inequality, if we don't change the sign. So we didn't change the sign. We took it to the other side. So we flipped the inequality, and we got a number of 4.5, right? So 4.5 is not an integral number. So it's not an integer number. We need an integer number. Okay. So this is roughly is equal to 5, right? So we can round it up to 5. So we take the number, the n, number of cycles as 5. And so we suggested that in the first two cycles, okay, in the first two cycles, we actually are not going to use we're not going to use 60%. We're going to use 70%. Okay, 70% decrements, which is going to be 30. So instead of so we basically just multiply by 0.3 directly. So we take the 5% again, multiplied by 30. So basically take 30% of the 5%, which is 1.5%, and then we take another 30% of the 5%, and we already get the 0.45%, which is already lower than the 0.5, which is the target. So we have reached the target by the first two cycles. So that gives us a number of cycles of 2. And so next we need to calculate the time. So the initial time is 20 minutes, but 10% faster each cycle, okay? So at each cycle, at each of these 5 cycles, we get 10% faster, okay? That's how the time works. So we have 20 instead of 100, so 20 times 5, that's going to be 100 minutes, okay? What if we decrease at each 5, okay, at each cycle, we decrease by 10%. We decrease this 20 by 10%, okay? Decreasing the 20 by 10%, so this is going to be 100 minus 10, so this is going to be 90%, okay? So we multiply the 20 by the 90%, as we represented it here. And so we put 5 cycles. So we got the first, second, third, fourth, fifth. And then this is obviously a geometric series sum. So we just use the geometric series sum rule, and then to add them all together. And we get our time in minutes, 81.90 minutes, which is the time that it's gonna take instead of 100 minutes, since we decreased by 10% at each cycle. And yeah, that was everything for the assignment. Thank you so much for paying attention. And yep, my name is Yarab Al-Hasi. I'm E230 for 3